In this lesson, we're going to be revisiting the idea of rates of change. This is a theme that's going to be recurring throughout the course, the idea of rates of change, and just refreshing our memory. It is a very important concept, and it leads into some even more important concepts when we get to the calculus course. Now, when we talk about rate of change, remember that the rate of change is just the slope. So that is the first thing to keep in mind. The second thing is function notation. So instead of saying y2 minus y1, well, this is the second y coordinate is the function at b, y1 is the function at a. The second x coordinate, the first x coordinate. So in other words, the points here, my first point is a f at a, and my second point is b f at b. So these are xy, xy. We're just finding a slope. There's another way that we can do this, and it is still finding the slope. It's just taking a little bit of a shortcut, and it's known as the difference quotient. And in general, we use the difference quotient when we're looking to find the slope of the tangent. Now, it's of course only going to be an estimate, and so you could argue that I should have indicated here that this was an estimate. Okay? But the important part here is that we are estimating the slope of the tangent line. We are using the slope, and the only thing that's different here is that we've condensed the idea of b minus a. We simply said that there's a difference. The difference between b and a is equal to h. So this b minus a, that's equal to h. And if b minus a is equal to h, then if I rearrange this, then b is equal to a plus h, and that goes right there. So it's not a great mystery where this comes from, although when you're first seeing it, it might look a little bit strange, and that's why I continue to talk about it in terms of the slope, so that you can remember that, keep that in mind. Okay, so other than that, which is really just review, I wanted to cover something that's a little bit new, which is this question, which I think is a valid question. It's a question certainly that the students have asked me. Because we're just doing estimates, how do I know whether or not my estimate's good enough? Now, I've talked to you in class and in these lessons about the idea that if you choose a small enough value for the difference quotient, if you choose a small enough value of h, actually I say here, improve the estimate by choosing smaller values of h. If you choose a small enough value, you should come up with a reasonable estimate. And if you choose the smallest possible value for h that you can calculate, you should come up with actually quite a good estimate. But is there a way that we can actually put a number to it as far as it being good enough? So from science, a concept exists called the percentage difference, where you're basically saying, well, how much is my estimate or my experimental result? How much does it differ from the correct or the accepted result? Now, unfortunately, we don't know what the final correct answer is. So what we're going to do is we are going to treat our better estimate as the accepted result. So that means the value with the smallest h. And then the next closest estimate, it will go here. And we'll use that to see how big a difference am I getting as I make successive changes in h. And that will be our standard for deciding whether or not something is good enough. So I think that might be a bit to take in. The best way to do this is to illustrate it. So we're going to estimate the instantaneous rate of change for x equals 4, but I want to do it within 1% for this particular polynomial. So the within 1% part, that's really what I want to focus on with this example. The rate of change should be relatively simple. So let's start off. I'm going to set my h value to be something quite small, 0.01. So I would expect that that's going to give me a pretty reasonable rate of change on a polynomial, but of course it depends on what the shape of the curve looks like at this point x equals 4. So my instantaneous rate of change is approximately equal to f of, I'm just going to write it out to remind us, f of a plus h minus f of a, I'm doing a following interval, over h. Now let's put that into the values we're using. Our a value is equal to 4. So f of a plus h is 4.01. So we get f of 4.01 minus f of 4 divided by 0.01. Now when you do something like this, you're going to want to make sure you do the entire calculation on your calculator. And so I've got mine handy here, and I'm just going to run through this. Now, the other thing is, make sure you don't do any rounding at all. Keep all of your calculations on the calculator until the very end. So I've done this in advance just to make sure it works out, but I'm going to do it again. So I've got 2 times, now instead of x, I'm going to replace it with 4.01. So that's going to be 4.01 minus 3, and then 4.01 minus 2, and 4.01 plus 5. And it turns out, with no rounding at all, this turns out to be 36.582402 minus, and f of 4, it turns out, is equal to just the integer 36 divided by 0.01. So subtract 36, divide by 0.01, and I end up with 58.2402. So that's my instantaneous rate of change estimate at x equal 4. Now we're going to do the exact same, we're going to do the exact same process, except for this time we're going to choose a smaller interval. I'm going to set h equal to 0.001. And so I'm still going to use an a value of 4. Now my a plus h is equal to 4.001. My instantaneous rate of change is approximately equal to f of 4.001 minus f of 4. This time my h value is 0.001. So I go through this again. Same calculation as before, except for now I'm going to use 4.001 here. So 2 times 4.001 minus 3, 4.001 minus 2, 4.001 plus 5. I'm going to get a value that's pretty close to 36. And in this case, once again, I ended up with 36.058024. And I actually, once again, didn't have to do any rounding there. And I really should say these are all approximate instantaneous. None of these are the actual instantaneous rate of change. They're all approximations. Divided by 0.001. But normally, I would go straight from here to here. I don't want to be writing down values if I have to do any rounding, because otherwise I'm going to lose precision. So I have to subtract 36 from that, and then I divide by 0.001, and I end up with 58 point, actually it looks like there was some rounding there, but because I kept all the digits on my calculator, I ended up with 58.024. Now an 02 showed up there. I wonder whether or not, I don't know whether or not that was a rounding error or whether it's something that got introduced by my calculator. I'm going to go through that again. Sorry for the extra time. 2 times 4.001 minus 3, 4.001 minus 2, 4.001 plus 5, minus 36. Yes, there were more digits there. Divided by 0.001. And the actual answer this time is 58.024 0.002. You can see those are awfully close to each other. Could be that I gave too good an estimate. So now let's go ahead and figure out our percentage difference. So it's going to be the absolute value because we don't care about positive or negative. And so it's going to be, let's just go back and remind you, it's accepted minus the estimate over accepted. This part doesn't actually matter because we're taking the absolute value. You can reverse these. But I'll do it this way. So we're treating this as the accepted. 58,024,002 minus 58.2402 divided by 58.024002 all times 100%. And so from that, I end up with, let's see, subtract 58.2402, and that's a pretty small number, divided by 58.024002 equals times 100%, and I ended up with an answer of 0.37%. So you know what, I mean, I thought those numbers were starting to look awfully small, but 0.37% is the difference between these. I was looking for the value within 1%, so I am within 1%, and although I don't know that this is the accepted value, it is reasonable to assume, so this is a reasonable to assume we are within 1% of correct answer. Now, it is an assumption. This is not absolute. I'm not 100% certain that this is within 1%, but if I went to an H value of 0.0001, this percentage difference would be even smaller. And so I think it is quite reasonable to say that I'm within 1% of the correct answer. If this was 0.99%, then maybe I'm within 1.5 or 1.25%. But because this is considerably smaller than 1%, I'm pretty confident about that. So that's an example of how you can estimate your instantaneous rate of change to within some specified threshold value. Still a good idea to start with small numbers. Sometimes your calculations might end up being such small numbers that you might get an approximately 0% difference. Well, that's fine as well. That means that your estimate is as good as you're going to be able to make it. A couple of other important rates of change just to mention, and I think I've mentioned these before both in videos and in class. The rate of change of distance is speed. That's a pretty common one. And the rate of change of speed is acceleration. Those of you who've done physics will be familiar with this. And just a reminder, at any turning point, which is a minimum or a maximum, the instantaneous rate of change will be 0. Or if you're estimating it, it's going to be a number that's really close to 0. And that's it. Pretty short lesson. Really, the focus of today's lesson was just to look at that idea of a 1% threshold or any kind of arbitrary threshold.